just carbon and H2O, water. Exactly, perfect. So let's see, someone had a question in the chat. Yeah, charcoal. So remember, whenever we break something down, you got to remember, I believe Dr. Alexander mentioned this in his lecture about the law of conservation of mass, where you must end with the same amount that you started, or you must end with what you started. So for example, if we're just breaking down sugar, which is just carbon, hydrogen, oxygen, we need to end with those elements. And in this case, we end up with a carbon and water. You don't have to worry about the specifics of the reaction. Just know that, when we break it down, it becomes charcoal, which is just pure carbon, and H2O. So going into the true and false. So the properties of a compound are similar to the properties of the elements of which the compound is composed of. Is that true or false?
False.
True.
And well, it's false actually, because a little example I like to give
Oh wait, yeah.
is so a good example I like to think of to kind of remember this is this. So think of sodium chloride, your table salt, right? So I don't know if you guys remember in high school if your teacher showed you the video of people throwing your alkali earth metals, your group 1 elements, into water, and they tend to blow up. And sodium is one of those elements. So you have an explosive metal, and you have chlorine, which is like a poisonous gas. So they're both pretty dangerous elements by themselves, if you think about it. But when they're combined, we have like a nice table salt. So that's a good way to remember that this statement here is false. Going on to number 10. Which are more numerous? So which ones are you more likely? Oh, let me clear that. So which are you more likely to find in, so like anywhere in nature? So the pure substances or mixtures?
Mixtures.
Mixtures.
Right, mixtures, because everything just tends to be stuck together, right? Even you look outside, everything's a mixture, right? So going on to 11, which are more numerous, heterogeneous mixtures or solutions?
Solution.
Heterogeneous mixtures.
Yeah, heterogeneous mixtures, because remember, solutions are, you can think of them as pure substances almost, as in liquid form, or in a homogeneous mixture, meaning it's evenly spread out within the solution. So this is, I was going to put HET mixture. So remember, a big example of this is the ocean, right? It has a lot of salt, it has a lot of other things like the animals that live in there, the stuff that comes off of them. But it's not like, perfectly evenly mixed, right? You can't just see through it. So it's a good example of like a heterogeneous mixture there. So going on to the next one, number 12, which are more numerous, elements or compounds?
Compounds.
Yeah, right, compounds, because we see them like bonded to almost anything and everything, right? And pure elements, you'll mostly find them like in mines, right? Because they're much harder to find. So on to 13, which are more numerous, metallic elements or non-metallic elements?
Metallic element.
Yeah, correct, metallic. So for those of you that might be thinking, why not non-metallic elements? We don't really see that many metals. Well, that's because, think about it. When we think of metallic elements, we mostly think of them as ions. So look at your blood. Like our blood has a lot of iron in them. Or you could look at limestone. You don't think of it as a metal, but limestone is calcium carbonate. So calcium is a metal, so it counts as a metallic element within that stone. So I hope that example kind of helps you guys out. So going on to number 14, name 3 pure compounds that you can buy at the store. So anything that you can buy, it would just be that compound alone that you can just buy off the shelf.
Baking soda.
Yeah, baking soda. So which is sodium bicarbonate.
Salt.
Salt, which is sodium chloride. I'm just gonna write the symbol just to make it simple. And one more thing, who can think of who can think of one?
Water?
Sugar.
I guess, yeah, sugar. So water, if you were to say distilled water, you'd be right. Because typically when we buy bottled water, it comes with like some chlorides just to help, kill any microbes. And some other stuff to make us like not die. Because if we were to drink pure water, it'd be pretty bad. But if you were to say distilled water, yeah, you'd be correct. But yeah, this is good. So sugar, table salt, and baking soda. And on to number 15, what are 2 pure elements that have practical uses? So like, what pure elements do we use that we can use in everyday life?
Aluminum and copper.
Right. We use aluminum for, aluminum foil. And copper for wiring, right? So we use copper to wire our homes, wire electronics, and so forth. So let's see, Jeremiah, if you can please scroll down. Oh, this is just the elements. All right, perfect. So next is just label the elements. So what's the symbol for hydrogen? Labeling our elements.
H.
H. And going down the line, what about for helium?
He.
He.
And carbon?
C.
Now nitrogen?
N.
N.
Oxygen?
O.
O.
Fluorine?
F.
EF. And then neon?
Ne.
Sodium?
Na.
Magnesium?
Mg,
M.
Aluminum?
Al,
Silicon?
Si,
Perfect. And phosphorus?
C.
Sulfur?
S.
Chlorine?
Cl.
Argon?
Ar.
Potassium?
K,
K.
Calcium?
Ca.
K.
Perfect. Titanium?
Ti,
Chromium?
CR.
Yeah, Cr. Perfect. Iron?
Fa.
Fe,
Fe? Cobalt?
Co.
Co? Nickel?
Ni.
Copper?
Cu.
Zinc?
Zi.
CN.
Yeah.
Zn. Oh, Zn.
Don't worry about it. Arsenic?
As.
Bromine?
Br,
Strontium?
Sr.
Sr? Silver?
Ag.
Ag? Tin?
Sn.
Yeah, Sn. Yeah. These elements, I kind of don't like how some of these elements their wording don't match the symbols, but it is what it is. Iodine?
I.
Barium?
Ba.
Ba? Tungsten?
W.
Yep. Platinum?
PT.
PT? Gold?
A.
U.
Yeah, perfect. Au? Mercury?
HG.
Hg? Lead?
PV.
Pb? And xenon?
Xe.
Uranium?
U.
And finally, plutonium.
Pu.
Yeah, perfect. I know it kind of seems redundant, but it is very important to just, get good practice of memorizing your symbols once you start working with them. But yeah, that's perfect. And
I
go ahead, Joey.
I'd like to add something real quick. So actually, a lot of these elements you'll be seeing a lot of like throughout the semester. So like what Alan was just saying, it's really good to have them, I guess, like repeatedly stuck in your head. Also, I guess it's a fun fact, but like some of the ones where like how Alan was saying he doesn't like how the symbols don't go with the words. A lot of these words were made based off of a Latin or a Greek word before in its time, like silver, Ag. In Latin, it's argentum, or like gold, Au, it's aurum. So like that's how a lot of those words were like came about at the time.
Also, I don't know about anybody else, but if you ever have a hard time remembering forgetting, like for me, I always confuse silver and gold. Just remember that Mr. Krabs laughs in silver. Anyway.
Okay,
That's
actually,
a
that's really
good
good,
one.
Sophia. I like that one.
Can you repeat that? Because I didn't hear it.
It was Mr. Krabs laughs in silver. And I wish I could- yeah, I love that one.
Yes, Mr. Corral.
All right. So the next thing up on the list for that's still technical, that's in module 1, would be scientific notation. So scientific notation, it's like important for us to get in the practice of it. So for this, starting with the first one, the 965,000, how would we go about turning this into the scientific notation?
You move the decimal and up and towards between the 9 and 6.
Okay, so we put it in between the 9 and 6. So so it will be 9.6, right? So will it be 9.6, 9.65, or like are we going to keep all this
9.65 and then times 10 to the 5th.
times 10 to the 5th? So why do we put the 5 here in this case?
The 3 significant numbers.
Because there's 3 significant numbers, right? Perfect. So moving on to the next one, which is 602 to the, I don't know, quintillion. Sextillion, sorry, 602 sextillion. So what would be our scientific notation for this one?
6.02 times 10 to the 23rd.
6.02 times 10 to the 23rd. I think that's what I heard, right?
Yeah.
Okay. So what other number is times 10 to the 23rd? Oh, wait, I don't think you guys learned that yet. Never mind.
Avogadro?
Yeah, Avogadro's number. Beautiful. You didn't even need to know that yet, but yeah. So it's actually the same exact number right there. 6.02 times 10 to the 23rd. So it's like a good reminder. So the bottom left one, what would that one be?
3.5 times to the -3.
All right, perfect. And then for the last one here?
1.60 times 10 to the -19. Right?
Yes, perfect. Okay, so I think it's safe to say that we all know how to do scientific notation. So moving forward, let's try multiplying and dividing it. So starting with this first one, how would we multiply this? Or how would you guys start with multiplying this?
You would actually, the ones that have the tens with the different power, since they have the same base, you would add the bases. And then you would actually multiply the 2.3 and the 7.4.
Okay, so 2.3 times 7.4 gives us?
I got 1.7.
Okay, and that was after you moved the decimal.
But yeah, I
Yeah.
moved the decimal.
So when you move the decimal over, that will make it 1.7 times 10 to the 10th power.
Uh-huh.
So why'd you make it 1.7 instead of something else, I guess?
Because when you're multiplying, you look at the less significant figures you have,
Okay, and
and it's 2. Because when you add, you look at the significant figures after the decimal.
yeah, you're right, Itzel. Sorry, I was reading Monte's question.
Oh, yeah, it's okay.
So
I got the chat, Jerry.
okay, cool. But yeah, so basically what you would do is you multiply the coefficients first, and then that will give you an answer, and then you convert it to the significant amount of figures like Itzel just said, which will give us 1.7. And then you just, if you move the decimal point to the left, you're increasing the exponent here. If you're moving it to the right, you're decreasing the exponent over there. Does that make sense to everybody?
Wait, so is the answer 1.7 times 10?
Times 10 to the 10th.
Oh, okay.
Wait, actually, let me rewrite that. times 10 to the 10th. All right, so moving on to the next one right here. What would be our coefficient? Or the non-10th power number?
Would it be 0? Because they kind of cancel out.
The coefficient or the times 10?
The coefficient would be 16.0132 before doing anything to it.
Yeah, before doing it. Yeah, for the coefficient. So the coefficient is this part that's in front of the like times 10 to the whatever. Yeah. Mm-hmm. So that was 16 point what? I'm sorry?
0132.
Okay, so 16.0132. And then, so from there, for number 2, does it say that it needs to be in scientific notation?
It just says give it in the correct number of sig figs.
Yeah, and the correct number is sig figs, right? So we don't need to change this to scientific notation. So how many significant figures, or what's the least amount of significant figures that we have?
3.
Okay. So what would our answer be?
16.0.
16.0, perfect. Yeah. Because we still need that 0 after the point to signify our third significant digit. Everything clear? No questions?
Yes.
All right. So moving on to this bottom right one right here, 5.5672 times 10 to the negative third divided by 7.1 times 10 to the ninth. So looking at the coefficients, what do we get before moving the decimal?
0.78, and then it's like kind of long.
Okay, 0.78. And you chose 0.78 because?
The least amount of sig figs.
Is 2. Perfect. Loving this. Okay, and then for the, so in order for this to work, actually, let's leave that to the side for a second. So the tens, what would that be? Like, what would the exponent be?
Negative 12.
Negative 12.
Negative 12, right? So it's times 10 to the negative 12. What are we going to do with this coefficient right here?
Move it to the right once.
Okay, and since we moved it to the right, what's going to happen to the exponent?
It's going to turn into negative 13.
Negative 13. Beautiful. Perfect. Any questions on that example? Or
Is that a
problem?
negative 17 or a negative 12?
That's a negative 13. Actually, let me rewrite that. Sorry, I write just a tad too big. Okay.
Can I cut in with something real quick, Jerry?
Go for it.
So we've been writing it times 10 to the exponent, right? Let's do 23. Why not? What happens if the problem gives it to you, or shoot, I goofed. What if it gives you e to the 23? Let's say it gives you 6 times e to the 23. What does that mean? Does anybody know?
It's the same thing, isn't it?
It's the same
Same
thing.
thing, right? So be careful. I actually had some students ask, so just know that this is the same thing as 6 times 10 to the 23. Just so you're aware. That's all I wanted to say.
All right. So next question. So 9.65 times 10 to the fifth over 1.60 times 10 to the negative 19. What does that give you? Or the coefficients, what would the coefficients be? Sorry.
6.03.
6.03. Okay. And then times 10 to?
24.
24, right? Because 5 minus, because it's being divided, negative 19, is actually adding, which will give us 24. Any questions on scientific notation? Everyone's good on it?
How come, I'm so sorry, how come we didn't make it to the 25? Oh, because we didn't move the decimal. I see. Never mind.
Yeah. Nice. All right. Cool. So for number 3, basically what it's asking is for us to make it so that this 10 to the whatever power becomes 1. So for 10 to the negative third power of liters, what can we convert that to make it 1?
Milliliters.
Milliliters, right? Because that will equal 1 milliliter. And then 10 to the negative 9th meters?
Nanometer.
Nanometer, perfect. And then times 10 or 10 to the third amount of grams?
Kilograms?
Kilograms, perfect. So this goes back to that chart where it starts with kilo, then it is kilo, what, deci? No, deca. Kilo, deca.
Trying to go up or down.
I'm starting from the top and working my way down. King Henry, kilo. What's the
Deci, centi,
Milli.
milli, micro, nano, pico.
Dang, you guys like jumped all those big, but that's fine.
But like going up is just like
It's
know
'cause
my
the-
gamer tag. Like
No,
kilo,
my gamer.
Kilo.
mega, giga,
Kilo,
tera.
mega, giga, tera. It's also the way the storage works on your computer. Fun fact.
Yes, exactly.
Well, I mean, that's literally dimensional. Okay, yeah, that's literally dimensional analysis. Cool. Yeah, I don't know who wrote that, but yes, the E stands for times 10 and then whatever. That's how you'll see it on your calculators when you start to input it for your exam. Oh, Sophia, nice. So the next one, correct number is sig figs. We have 253.8 grams being added to 7.8459 grams. So how far? So how will we figure out the correct number of significant figures for adding?
When it's summing or subtracting, you take the least amount of decimals you have.
Yeah, the least amount of decimals, right. So which one has the least amount of decimals?
The 253.8 grams.
0.8, perfect. So basically that means that we're only gonna go to the 10th place or like out 1. So what exactly will we get then? Like for our answer.
160.8.
260 what?
1.6.
0.6, yeah, grams. 8 plus 8, 16, which is why there's a 1.6. And then 4 is less than 5, so you'll leave it as 0.6 grams. And that will be your answer for that one. Any questions for adding it and subtracting here? No? Self-explanatory, I think. I don't know. Sound good? Cool. So, number 5, if a sample of a substance has a mass of 23.212643 grams and a volume of 12 milliliters, what is its density? Give the answer and correct number of significant figures. So, what is density, guys?
Mass divided by volume.
Mass divided by volume. So, since we're dividing, how are we going to figure out how many significant figures that we have?
The least amount of sig figs.
Okay, which is?
2.
2, right? Okay, so 23.212, et cetera, divided by 12 will give us?
1.9.
1.9. Does everybody agree with that?
Yes. Yes.
Okay, so is it just 1.9 or like what units do we have?
Grams per milliliter.
grams per liter.
Grams per
Grams per milliliter.
Yeah, milliliter.
There you go. So make sure to always put your units after you figure out what your answer is asking for. Because if you don't, or like if you accidentally solve for the wrong units, it can you can end up getting the wrong answers too. So it's really important that you remember what units you're using. Now, going to number 6, 5 inches into centimeters. So how many inches or how many centimeters are in an inch? I'll give you a hint. It's right here.
Two point
2.54 centimeters. All right. So how are we going to figure out how many centimeters we have then?
Multiply 5 by 2.54.
Okay. So multiplying 5 by 2.54, what will that give us?
12.5.
12.5, right? Is that what you said?
Wouldn't it be 12.7?
0.7, yeah.
12.7. So it says to give it an incorrect number of significant figures, right? So how many significant figures do we have here anyways?
So then would it be 13?
Yeah, it would be 13 because we only have 2 significant figures because of the 5.0 inches. So 13 centimeters. Moving on to the next one, we have 1.00 ounces converted to milliliters. So this is the conversion we have. So with this 1 ounce, how many milliliters do we have?
So then can we divide 12 by 355?
Wait, can you repeat that?
Because we're looking for 1 ounce, and if it's 12 ounces equals 355, then wouldn't we just divide 12 by 355? See how many milliliters are per ounce?
Will be 29.6.
49.6.
29.
29?
Mhm.
Okay, that makes more sense. Yeah, I think 29.6. So what I'm guessing you were saying was 355 divided by 12, right? I think it was Esmeralda or Vivian, one of you.
Oh, yeah, sorry.
No, you're fine. It's just like math words confuse me. But yeah, it'll be 29.6 because we have 3 significant figures here, 3 significant figures here, 3. So we'll have 3 here, 29.6. Now, moving on
Ooh,
to
dangerous game. Wait, Jerry, before you go.
What's that?
When you're doing conversion factors, you should never use the significant figures of your conversion factors because they're ambiguous numbers and they have
Oh,
an
no,
infinite number of significant figures.
I was doing it from this.
Yeah, but just because you said 3 and 3, so just heads up for everyone. Don't use the significant figures of your conversion factors. Always use the ones from your given number.
What she said. I didn't even know that actually. But yeah, so we're converting to 1 tablespoon to milliliters. So how would we be able to do that?
So can we use our answer from the previous one? So 1 ounce is 29.6 milliliters. So would we just do 29.6 times never mind. I kind of lost my thought. I am so sorry.
No, you're fine.
That times 2, no?
Wait, times 2 or divided by 2? I'm sorry, you cut off?
You would divide by 2.
Divided by 2, right? Because for tablespoons, it's 2 tablespoons.
Yeah, there you go, Jerry. Yeah.
For
It's TBS for tablespoons, but
TBS, potato. And then that goes to ounces for every 1 ounce. And since we already have how many ounces there are in a milliliter, you can literally just throw that in. So you'll be dividing that by 2.
Oh, so 29.6 divided by 2?
Yes.
Okay, thank
Which
you.
will be so what would your answer be? Sorry.
14.8.
14.8. So how many how many significant figures do we have here?
2.
2. So it'd be 15.
15. Yeah. It's just good to get in the habit.
Wait,
So,
can you explain how you got there one more time? I got lost in the math.
So basically what everyone or what they did was we already had the ounces. So we started off with the 1 tablespoon TBS apparently. And then from there, we converted from tablespoons to ounces. And then since we already know how many ounces are in a milliliter, we basically divided the 29.6. 29. That's a 2. Let me rewrite that actually. We divided that by 2. To get us our milliliters. Does that make sense?
Can I ask, how come you put 1 ounce on the bottom again?
Yeah, so basically we're taking the 1 ounce that we got from our previous answer that equals 29.6 milliliters, and we're putting that for this ratio here.
Oh, I see, because 29.6 is equal to that.
Yes.
Okay, thank you.
Uh-huh. Any other questions about the tablespoon, the ounce, or tablespoon of milliliters? No? All right. So moving to the next question. How many liters are in 25 milliliters?
Zero 0.025.
0.025, which is also 2, what do you call it? 2 significant figures. So that just happens to sum up nicely. 1.732 kilograms to grams. What do you guys get for that?
You multiply the kilograms by 1,000.
Okay, and that gives you?
1,732.
1,732. Oh, cool. All right. And then 655 nanometers to meters. This one, you can put in scientific notation if you want. Only because it's like, there's that many zeros. So it's up to you guys. But how many meters are in a nanometer? Or how many nanometers are in a
1 times 10 to the negative 9.
1 times 10 to the negative 9 meters equals a nanometer, right? So basically, instead of putting that 1, we could just put in this 655. So 655 times 10 to the negative 9 meters equals 655 nanometers. So is that in scientific notation, or do we need to change something?
You need to move the decimal.
Right. So 1, 2. So it will become 6.55 times 10 to the what?
Negative 7.
Negative 7
Sorry.
meters. Perfect. And last but not least, number 7. So suppose that you have a gold brick that has the dimensions of 4 centimeters by 8 centimeters by 16 centimeters. The volume of the brick would be 512 centimeters cubed, or 512 milliliters. Compute the mass of the brick in grams if the density of gold is 21 grams per milliliter. What is the mass of the gold brick in kilograms? So, what would you guys want to do or start with? So what's the question asking for actually?
I want the mass.
It wants the mass, right? Okay, so do we have any units that happen to have grams in it, since that's what we use for mass?
The density of gold.
Yeah, the density of gold, right? It has grams somewhere in there. And so for the density of gold, it has grams, but it also has milliliters in it, right? So what other information do we have that has milliliters in it?
The volume.
Okay, and so what's the volume?
512 milliliters.
512 milliliters, okay. And so we have 512 milliliters. So in order to get rid of this milliliters, what are we going to do with that density of gold? Are we going to multiply, divide?
Divide.
Divide?
Wouldn't we multiply because we're already given the density?
Yeah. So basically, since we're multiplying it, that would mean that we're putting the 21 grams on the top and the milliliters on the bottom per 1 milliliter. So the milliliters will cancel out because units have to cancel out in order to be like gotten rid of, basically. So we'll multiply that 512 by 21, and that will give us
10,752.
10,752?
Yeah.
Okay, and that's grams.
Yeah.
So are we done?
No, because it's asking you to know the mass
In kilograms.
In kilograms. See, I had just mentioned that earlier. Boom. In the practice. Okay, so in order for us to get to kilograms, what would we need to do?
Multiply by 1,000.
Multiply by, oh wait, multiply or divide? There you go. There you go.
Divide.
So 1,000 grams by kilogram. And what do we get?
$10.752.
10.752 kilograms. Perfect. Any questions?
Do our sig figs matter here or no?
I mean, it doesn't say, so like, it's like up to you. It's up in the air if you want to.
But if you had to, how many would you say you needed?
Yeah, what would it be then?
Just 11.
Was our given?
Don't you, or aren't you supposed to, isn't it supposed to be like in between 1 and 10? So like 11.
That's for, I think you're talking about scientific notation.
Yeah.
Yes. Oh, so then we'd just be 11?
Okay, so our given was the 512 milliliters, right? That's what we started off with. And then we used the density to convert. So our given, how many significant figures do we have for our given here? Or the first thing that we started with? Top left.
Oh, 3.
3, right? So since we have 3 here, what would be it down here?
10.8.
10.8 kilograms. Perfect.
So whenever it's like that, you only use the first, like, I guess the conversion that you use, that will be your base for the significant figure? Just.
Yes.
Okay.
So anytime you see units that aren't by themselves, they're normally meant to be like conversion rates. or conversion factors. So if you see something that has a unit by itself, like in this case, milliliters, it was just milliliters. So we could use that as our starting point. And then we can go into the density to get to grams, because the grams per milliliter helped us to get rid of the milliliters. Does that make sense? Any questions on the last two question sets that we've done? No? Pretty simple. Well, all right. So with this, we're going to go into question set 3, which I forgot to look at the PowerPoint, but for this question set, for questions 1, 2, 3, 4, well, basically for this question set, it's what he talked about in lecture or the PowerPoints that he gave you guys. And the best way to remember it or to do it would be to just remember keywords about it, like conservation of matter. Well, when we talk about conservation, what would that be? Like saving, right? Like can't be created nor destroyed. Just as like a rule of thumb.
You're making sense, yes.
Awesome, great. Like the sound of that. So who would like to go next to go over 6 and 7? You can do it, Sophia.
I can do number 7.
Number 6, it's just the equation. Don't read too much into it.
I'm reading it. Hold, let me see.
All right.
Really put her on the spot there.
So, okay, for number 6,
I don't understand what it's asking.
Oh, it's this one.
For number 6, all it's asking for is the molecular formula.
Oh, no, I remember. Yeah, never mind. I remember this because I took Dr. Alexander. But
Go for it, Claudia.
no, I got it barely right. Okay, let's see.
Right is right.
Right is right.
Facts.
Like, I didn't get this one when I was in Dr. Alexander's. I got it because I guessed on it. Did I get it? Maybe not. Anyways, so when ammonia gas is decomposed into nitrogen gas and hydrogen gas. So I guess, what's ammonia, guys? I don't know if you guys, yeah, what's ammonia?
NH3.
Awesome. Does it have a charge? Does it have a charge or no, guys? This is just a trick question.
No.
No, it doesn't have one. Awesome. Okay, so it says that it's decomposed into nitrogen gas, which is N2, and hydrogen gas. Found that the ratio volumes of the gases is 2 parts ammonia and 1 part. Yeah, I literally hated this one. 2 parts ammonia and 1 part nitrogen and 3 parts hydrogen. But the volumes are measured under the same conditions of temperature and pressure. Show that if the molecular formula of ammonia is NH3, the molecular formula of nitrogen and hydrogen must be N2 and H2. You know what, Jeremiah, you take this. I didn't get this one.
All right. So honestly, this question's a trick question. I'm not even gonna lie. But basically what he's trying to say is show why, wait, let me.
It's a proof, like prove it.
Yeah. Why do we have a 2, or why is ammonium NH3? Why is nitrogen gas N2? And why is hydrogen gas H2? And basically what you would do is like, okay, we have 1 nitrogen, we have 3 hydrogens, we have 2 nitrogens, we have 2 hydrogens. And then based off of what he said, which is that ammonia is in two parts, which means that we'd have 2 here. That, okay, well, we're multiplying that 2 times the 1 and times the 3 for the hydrogen, the 1 times the 2 for the nitrogen, and then the 3 times the 2 for the hydrogen. That's on the right side of the equation. And so when you do that, you'll have 2 nitrogens and 6 hydrogens on the left side of the arrow, and you'll have 2 nitrogens and 6 hydrogens on the right side of the arrow. Sorry, that's supposed to be a 3 right here. So basically, 2 nitrogens equals 2 nitrogens, and then 6 hydrogens equals 6 hydrogens. So you're just adding up
Can
all
you go through that one more time? You kind of lost me there.
Sorry.
Yeah, don't. Yeah.
Okay, so when he says the 2 parts, basically what he's saying, I don't know if you guys have talked about moles or not yet, but basically what he's saying is that you have a 2 in front of this compound right here, which is ammonia. So since there's a 2 in front of it, we know that there's a invisible 1 subscript here. So basically what I did was I put these subscripts in the front, the 1 and the 3, so that we know how much of that element we have just from the equation itself. And then I did the same over here. So we have a 2. So I put the 2 in front of the nitrogen here. And then we have a 2. And so I put a 2 in front of the hydrogen there. And then, since it says the 2 parts ammonia, I multiplied the 2 times this times the ammonia compound. So I distribute the 2 to the 1, and then I distribute it to the 3. So it becomes 2 times 1, which is 2 nitrogen, and then 2 times 3, which is 6 hydrogen. And then I just do that for each element. We have 3 parts for the hydrogen gas. So 3 times 2 gives us 6 hydrogen. Does that make more sense?
Am I crazy, or is that basically just balancing the equation?
It is just balancing the equation.
Wow, I feel dumb.
So what's
No.
the actual answer?
It's because Dr. Alexander, when he put that, it just confuses me, even though.
So basically, you're going to put the balanced equation 2NH3 goes to make N2 plus 3H2. And then you're going to put that there's 2 nitrogen on both sides and then 6 hydrogens on both sides. Yeah. Because that literally, it's a proof. He literally gives you all the answers. I guess that was just so that you wouldn't need to go into moles. I think that was his reasoning behind that.
So is this question, does it just show you like different equations and you just pick the right one?
It shows you the equations. Basically, all you're doing is, it's like a math function, I guess. Like you're just making it equal each other on both sides.
No, I guess she means like in the exam, like I just have the question too, like
what
is
would
there
the like
any
the
way
answer choice
wiggle,
like does he want us to write it?
like plug it in how or chose between, you know, different options? No.
For the answer choice, I just say look for the ones that have the molecular formulas and or the chemical reaction. It's not a given that it will be on there, but I'd say that's like the most important thing. If any of what is on this page right now is on there, choose it because it's right. Any questions on this or any other questions?
So basically, we just break down the question, and then as we go, then we are just trying to make the equation equal to itself. That's how you got the answer, right? You're just breaking it down, pretty much.
Perfect.
Okay.
Beautiful
I have a question.
Go for it.
But okay, you know the 2 that you said you put in front of the equation and then you distribute it?
Uh-huh.
Where did you get that 2 from?
So I had a feeling. I got you. So in the actual question itself, he said that we have 2 parts of ammonia. So that means that we're multiplying this 2. It may be a little hard to see. That we're multiplying this 2 by the ammonia compound itself, which is why I put the 2 in front of the NH3. We have 1 part nitrogen which is here. And then we have 3 parts of hydrogen, which is why I put the 3 in front of the H2.
Oh, okay. So then if it were to be another different number, then you would just do the same with that number.
Yeah, so basically whatever parts it is what you're multiplying to the entire compound.
Oh, okay, thank you.
Uh-huh. Any further questions? All right, well, without further ado, I'll let Sophia take the stand. I think it was Sophia.
Yeah, I'll do number 7.
Go for it.
All right. I guess we'll just write the molecular formula. What's the molecular formula for water?
H2O.
H2O. Yay. Okay, I'm gonna do this real quick because what's the molecular formula for ammonia?
NH3.
NH3. And then what about methane? Oh, first of all, before I ask you the formula for methane, does anybody know what's special about methane? What kind of compound is it?
Wait, is it polyatomic?
Not polyatomic. Because polyatomic means that it has a charge, right?
It's ionic, no? Molecular.
Okay, well, ionic bonds are between a metal and a non-metal.
Oh.
But I heard somebody say molecular. You're not wrong.
Okay.
Molecular is between 2 nonmetals, right? But then methane is a special kind of molecular bond. Does anybody know what kind of special molecular bond it is?
Isn't it alkane?
Alkane, yeah. An alkane, or does anybody know what the other name for the alkanes are? What is an alkane made up of?
Is it like alkaline earth metals, or like is that what you're talking
What was that?
about? Is it like alkane earth, like made of like carbon and hydrogen?
Yeah, carbon and hydrogen. I have someone in chat. Yes, hydrocarbons, exactly. So alkanes are special because they're compounds made completely of just carbon and hydrogen. So the other name that they call it is hydrocarbons. Hydro for hydrogen and carbons for carbon, right? So methane is a hydrocarbon, and there's a special rule for naming hydrocarbons, right? And actually methane is one of those special exceptions. Does anybody know what the exception is? Or, okay, how do we normally name covalent bonds? Do we use prefixes, suffixes? Who knows? We just name them Panchita.
Prefixes, no?
Well, covalent bonds are, they share electrons, so they have nonmetals and nonmetals.
I heard somebody say prefixes. And
Yeah.
yes, they do. We do use prefixes, right? So there's like the mono, di, tri, right? But with hydrocarbons, do we use mono, di, tri, and tetra?
No.
No, right? Because organic chemists hate us. Anyway, so then how do we name the first 4 types of hydrocarbons?
Methane, ethane, propane, and butane.
Methane, ethane, propane, and butane, right? And that's Mama or Maria eats peanut butter, right? So then what is the formula for methane?
CH4.
CH4. Does anybody remember the formula for finding the number of hydrogens in a hydrocarbon in general?
H2N plus 2?
Yeah, exactly. So you're gonna do N is the number of carbons, right? So depending on how many carbons you have, you're going to put that in the number of carbons, right? And then to find the number of hydrogens, you're going to multiply that by 2, and you're going to add 2. Yes? Does that make sense? So then that's why we have 1 carbon, right? That's methane. So then 2 times 1 plus 2 gives us 4, and that's why our formula is CH4. Yes? Okay, cool. And then last but not least, carbon dioxide. What's the formula for carbon dioxide?
CO2.
CO2. Yes, awesome. Does anybody have any questions about naming compounds and writing the formulas? Yes, Jonathan, you had a question?
Yeah, how do we name hydrocarbons? So what was that prefixes?
Okay, so it's gonna be, except for, sorry, hold on. Except for the first 4 hydrocarbons, you're gonna use the same ones as always. So you're gonna go do penta, or just kidding. So the way that you're gonna know that you have a hydrocarbon is gonna end in A and E. So if you have 5 carbons, that's gonna be pentane, and then you're just gonna use those same prefixes from 5 to 10. But before that, you're gonna use these 4 names that you're gonna need to memorize. So that's gonna be with the mnemonic, Maria eats peanut butter, and it's methane, ethane, propane, and butane. Does that make sense? Awesome. Any other questions?
All right, so that's it for question set 3. And now we just have one more question set to go through, and you guys will technically be ready to get your A's for Dr. Alexander's first exam. So, Andre, did you want to share your screen, or did you want me to still share it?
No, can you share yours? Because I don't have the files on my computer right now.
All right, sounds good. Sounds good.
Thank you.
Mm-hmm. All right. So there we go. And go. Well, number 1 they just did. So.
Okay. Yeah. So we can do number 2, I guess. But is number 2? I feel like that's also like, I forget that Dr. Alexander kind of like skips like modules, I guess, because. But yeah, okay, it doesn't matter. So it says for number 2, it says draw valence structures of water, ammonia, methane, and carbon dioxide. So this is a key word right here, valence. Does anybody know what valence electrons are, or what that means?
The outer shells.
So yeah, the outer shell, and what about it? What about that outer shell is so important?
The amount of electrons that it has in it.
Exactly, right? So we're supposed to look at the valence structure for some of these elements. So we looked at water, and we already named that one, right? And that was H2O. So when you're doing your valence structures, you kind of you want to write your elements out, and then you'll write around it the amount of valence electrons in a dot form, which you'll learn about it later on in your workshops. But right now, hopefully he covered it already, and you guys should know some of it. Okay, so for those of you who have seen if Dr. Alexander has covered it, does anybody know how we would start for, like, let's say water? So water is H2O, right? So let's write. So first you want to choose by choosing what element's going to go in the center. Usually you want to keep the one that you never put your hydrogens in the center, because they can't make more than one bond, okay? So you never want those in the center. You usually want the one that can make the most bonds in the center, okay? So in this case, it would be oxygen. So let's draw our oxygen right here. And how many valence electrons does oxygen have? Okay, I see the chat. 6, yeah, it does have 6. So give me 1 second. I don't know why it's not letting me. Hold on. Maybe. Okay, so that's 6, right? So when you're drawing these valence structures, you usually want to go each side first. Like you want to cover a dot here, a dot here, and then a dot here. So you want to go all around the element first, okay? So you'd go here, and then it has 4 sides, so we already went through it once, and you want to go over it one more time because it has 6. So you'd have this. So that would be your valence structure for oxygen, right? So now let's get the valence structures for the hydrogens in it, okay? So let's draw a H right here, and for the sake of it, I'll draw the H over here. How many valence electrons does hydrogen have? One, right? So you could put that dot here. You could put it anywhere, but I mean, you'll see why I chose to put it here right now. And so you know that the same thing would be for this hydrogen, so you put 1 dot up here. And so when you're doing the valence structures, what you just want to do is connect these dots. And do you know why we're connecting these dots though? Or do you know why these compounds form these bonds and are connecting these dots?
Because hydrogen wants to give and oxygen wants to gain.
Exactly, right? So yeah, and so how many electrons, if you think about it, since they're sharing now, how many electrons does oxygen have in its last shell?
Since they're sharing, it would be 8.
It would be 8, right? And does everybody know how many electrons any element needs in its last shell to be stable?
8.
8, right? So yeah, and that's why you have 8 in total, and that's why that would be how water looks like, okay? Does anybody have any questions? I'm sorry?
I'm sorry, can I say something real quick, Andre?
Yeah, you're good. Yeah.
So for Dr. Alexander, you might see it with the electrons, you might not, but the most important thing is that you see the oxygen bonded with the hydrogen. Because
yeah.
That's how he might end up showing it.
Yeah, because since you guys aren't that far in yet, you might just see it like this. So without those little electrons, you could just see it like that and just make sure that, yeah, it's one little line and one little line on this. And it could look different ways. Like the hydrogen, this hydrogen could be all the way over here instead of here. It could be, just remember, it's got to be 2 hydrogens that are connected. Doesn't matter where, honestly, but just make sure that they're connected, okay? So that was water. So let's do ammonia now. So ammonia, I'll do it over here on the side because I feel like I have more space there. So ammonia is NH3, right? So remember, hydrogen can never be your center atom, so we can assume that nitrogen will be our center atom, correct? So how many valence electrons does nitrogen have?
Does it have 1?
So that would be its charge, I think, or it's you charge for another thing when you're doing like the oxide ions, I think, if you're getting 1, but it wouldn't be, it's not exactly 1 for its valence.
For the valence, wouldn't it be 5?
It would be 5, yes. Okay. It would be 5. So remember, you're doing each side, you want to cover each side first. So 1, 2, 3, 4, and then 5. Okay. So now let's put some hydrogens around it. So we know there's going to be 3. And you can write 1 over here. And you can write 1 over here. And like we've stated before, well, hydrogen just has 1, right, on its valence shell. So just put 1 dot. And then again, you can just make your bonds right here, and then connect your dots right there, right? And like I said, like how Jeremiah said, these are electrons over here, but it just depends on how Dr. Alexander decides to put it for you in the test. It might not have these little dots, it might not, but just make sure that overall your compound would look like that. So like a nitrogen with 3 little sticks around it and a hydrogen on the end of the other stick, okay? So let me clear this. So now methane. So for starters, what do you think for methane, what's going to be my central atom?
Your carbon.
My carbon, right? And how many dots am I going to need around that carbon?
4.
4, right? And let's say I were to do it like this. Would that be right?
No.
No, right? Remember, because even I gotta do, because it's a mix-up that happens quite often. So remember, you gotta go each side first. So it'd be 4, and then like that. Okay. And how many hydrogens is there gonna be in the methane?
gonna be 4.
Maybe 4, right? So you'd have 1, and so you'd want to surround your carbon with all those hydrogens. So you have 4, and this one's pretty nice. It kind of all connects together. You see that it each has 1, and it forms nice little bonds with each hydrogen. There's no electrons. There's no lone pairs or like lone electrons hanging around. It's just it forms a nice little symmetrical compound, right? So this would be how your methane looks like. So now let's do the last one, carbon dioxide. So carbon dioxide was what? What did we say it was?
It was 4. Carbon is 4.
Oh yeah, it was 4. Yeah, I was just asking like the CO2, but yeah, it would be 4 dots around it. So 1, 2, 3, 4. So this one might get a little not tricky, but you'll see what we have to do right now. Let me redo that. I feel like I did it too big. So yeah, you have your carbon here, 4 dots around it, and so you have 2 oxygens, right? And how did the oxygen look like?
There's 6.
There's 6, right? So 1, 2, 3, 4, and then 5 and 6. So we know that this oxygen will look the same. So 2, 3, 4, 5, and then I'll just do it over here just for the sake of it. But yeah, but it's 6 in total. Okay, so now let's connect our dots. So we can connect this one right here and this one right here. So if I were to leave it like that, would that be my answer? Do you guys think, or?
No,
No, right? Why would it not be my right answer?
because the middle one should be filled.
Yeah, the middle one and the oxygens, technically, they both should be full. So these 2 little elements follow some rule called the octet rule, okay? So this you'll see it later on, but I mean, it's nice that you're seeing it right now, I guess. So the octet rule, and can anybody tell me what that is, the octet rule? The definition of that. So it was kind of, I don't know who said it, I didn't see the name, but it was kind of what they said, that they said the middle one needs to be full. So that's almost exactly like the definition of the octet rule, okay? So certain elements, coincidentally, it is, in this case, it is both carbon and oxygen. There's some other ones, nitrogen and fluorine, that require a full valence shell, right? So right now it doesn't have a full stable one because it still has 2 electrons hanging around. So what do you think those 2 electrons and this one right here, because technically it's still, this one is unbonded and it needs to be bonded to be stable. So what do you think these 4 dots can do with each other? They can form, yeah, they can share again as well. So they can form another bond. So when they form another bond, we'll think of it as like being attracted to the other one. So pretend that that little electron I just erased would move a little bit over here. And then this one would also get attracted and move a little bit to the right of the carbon, and it would bond right there. Same thing with this one, just because how I drew it, it might be a little different, but yeah, think of that one moving all the way over here, and then think of that little electron being attracted to the other one being over here, and then they would form a bond right there. And so does anybody know what this is called, those little 2 lines?
Double bond.
Double bonds, right? And they would form a double bond. And like I said, so remember, I don't know how it's going to be in your exam, so it could be written in 2 ways, but just remember that carbon dioxide, it's a special compound that likes to form double bonds. So for sure, when you see your exam, make sure that it has 2 lines or not just 1, okay? Alrighty, so that's how you do valence structures for these compounds. Does anybody have any questions about that?
No, thank you.
Alrighty, I don't know.
I have a question in chat. I'm sorry. I just don't want to type it out. It says, can you explain how do you find the electrons of the outer shell? Because the periodic table that's on the back of the book does not have the numbers.
Sorry, what happened?
They sent it to me privately. Just
Oh,
how do you find the electrons of the outer shell?
how do you find the electrons on the outer shell?
I think it's the ones with the numbers with an A on it. I think that's the one, right?
Isn't that the group number?
I mean, also just I mean, the basically. So does everybody know what the vertical columns are called, right? The groups. So see, they're numbered. They're not numbered just well, not randomly. They have a certain. These elements are put in a certain way, because of those. They pertain to those certain numbers, like on the periodic table. So those 1, the 2, and then the 3, and then if you skip like your transition metals, you'll see that in the back of your workbook, it says like 3A, 4A, 5A, 6A, and all that. Those little numbers actually tell you the amount of valence electrons. Does that make sense? So like if you were to draw, let's draw lithium real quick. Like lithium, does anybody know how many protons lithium has?
Three.
3, right? So you know that in the little nucleus, let's just draw this as a nucleus. You know that it's going to have 3 protons, and then depending on what lithium you have, it could be a different amount of neutrons. But in this case, they don't really matter. It could be 4 neutrons, 3 neutrons. It could be something else. But let's just focus on protons and electrons for the moment. So it has 3 protons, right? So how many electrons will it have if it's like a neutral lithium? Or like an uncharged lithium? How many electrons do you think it's going to have? Do you guys think?
I'm sorry, can you repeat the question?
So we said it has 3 protons, so 3 of the little plus, so protons. How many electrons do you think it's going to have if it's like neutral lithium? So it's not a lithium ion, it doesn't have a charge, it's just regular lithium. How many electrons do you think it's going to have around it?
3.
3, right? Because 3 positives and 3 negatives would cancel out, right? So I already drew a certain amount of shells. I should have asked you guys why it would be like that, but it doesn't matter. So how many electrons can fit in the first shell? Does anybody know?
2.
2, right? So 1 right here and 1 right here. And how many can fit on from after 2? Like after 2, how many electrons can fit in each shell?
8.
8, right? But that really, yeah, 8 can fit, so that's correct. But in lithium's case, we only have 3 electrons, right? So we only need
So
to
it
put.
just be 1. Sorry.
Yeah.
I thought you meant in general.
No, you're right. You're right. In general, it would be 8. And yeah, in this case, so lithium only has 3, so it'd be 1 right here, right? So yeah, you were right. It's a little. So do you see how the valence is 1? If you were to do this, the valence electron is 1. So if you were to do the electron, and do you see how it's in group 1? Do you notice that little pattern? Like it's in group 1 and it has 1 valence electron. So if you were to do the same structure for sodium, you could even do it yourself right now. If you were to do it on a piece of paper, if you would do sodium, potassium, rubidium, cesium, and francium and all that, if you were to do those, you would get 1 valence electron in the last shell. So they could have more shells, like sodium has more shells than lithium, but the pattern is that in the last one, for all of those elements, it'll be 1 valence electron. So that's how you would figure out. Was that the question for starters? I don't even know if I'm answering the question that was even asked. That's what I understood from the question. Sophia, did I answer?
Me too. I haven't gotten a reply. I just don't want to call them out.
Oh, okay. Oh, yeah, well, hopefully. So yeah, but that would be how you, okay, good. Awesome. So yeah, that's how you figure that out. If you did the same thing for like beryllium, you'd see that the last one is 2 and all of that. And for boron, you'd see 3 and so on and so forth, okay? So hopefully that explained it a little better. But yeah, that's how you find your valence structures. So the next one would be what number? Does anybody want to do number 3, or because I feel like I've been talking for a while? If anybody wants to go ahead.
Sure, I'll go ahead and take over.
All right.
So we're on question 3, right?
Uh-huh.
Okay. So before we start breaking these apart, how do I what is an ionic compound and what is a molecular compound?
The molecular is the one formed by 2 nonmetals,
Mm-hmm.
and the ionic will be 1 nonmetal and 1 metal.
All right, so give me one moment. Let me just write molecular compound and then ionic compound. Okay, so here we said we have non-metal with non-metal. And then what about the ionic group? I'm sorry.
One metal and 1 non-metal.
Okay, so here we have a metal with a non-metal. So these are two ways to identify them, but there's another way. How do our electrons interact with each other in ionic and molecular compounds?
In molecular, they share?
Yes. Here our electrons are shared. And then what do ionic compounds do? What do the electrons do?
They take.
Yes, they transfer each other. Electrons are transferred. Okay, now that we got our general definition down, we can start breaking these lovely compounds that we have here into groups. So for NaCl, what is it composed of? What is this, and then what is this?
Sodium chloride.
Sodium.
So sodium chloride, yeah, NaCl.
Sodium is a metal and
Yes, so this one is a metal and this is non-metal. So what can we deduce from that?
so it would be an ionic.
Yes, it'd be an ionic compound. So NaCl is ionic. Okay, now H2O.
Molecular.
Why would it be molecular?
2 non-metals.
Yes, so hydrogen, this is I'm just gonna abbreviate it to NM because it's shorter. And oxygen, that one is obviously also non-metal. So this is molecular. Molecular. Okay, so we have H2O. Now CaCO3. Can someone tell me the name of this?
Isn't it calcium carbonate?
Yes, it is calcium carbonate. Calcium carbonate. And then, so this is carbonate, and then this is calcium. So what are these? What type of bond do they share? Or what type of compound is this?
Ionic.
Yes, it is ionic. This is a metal, and this is a non-metal. So therefore, this one is ionic. Okay, we're on our fourth one already. We're on a roll. Let's see, we have potassium nitrates. So potassium nitrate, oh shoot, I was supposed to ask you guys what the name was. Oh well, you guys got a freebie. So potassium and nitrate. So
Ionic.
okay, thank you. Yes, it is ionic. Straight to the point. Yes, ionic. So this is metal, non-metal, and then so sodium chloride. That's not sodium chloride. I said that wrong. What compound is this?
Molecular.
Oh, sorry, the name of the compound. Sorry.
Is it ammonium chlorine? Chlorine?
It is ammonium chloride. We still ended in "ide." So ammonium chloride. Okay, and he had said it was molecular. Why molecular?
Non-metals.
Yes, these are
They're all
non-metals.
non-metals.
However, ammonium. What does ammonium have that's different?
It has charge.
Yeah, it has a charge, right? And who are the only ones that have typically charges? What type of bonds or what type of compounds typically share charges?
Polyatomic?
Not polyatomic, are ionic compounds. our ionic compounds, remember our electrons are transferred here. And ammonium has a charge, therefore chlorine has a charge of what? What charge would chlorine have in this case? Let me write it right next over here. So ammonium has a +1 charge. This is a +1. So what charge does chlorine have to have in order to cancel out that charge?
Negative.
Yes, a negative charge. So what type of interaction would this be? What type of compound? Any guesses?
Would it be an ionic?
Yes, it would be ionic. And the reason why is because here our electrons are transferred. Although this is technically two nonmetals, this is still an ionic compound. So that one's kind of there to throw you off. Okay. Okay, and then our last one, so H2SO4.
Ionic?
Yes. Actually, that's weird. Why is it considered ionic, guys? Milliliters.
Which one?
Yeah.
Is it
H2SO4.
sulfur, like hydrogen, sulfur, and oxygen?
Yeah, well, it's because I have the key here next to me as well, and he says it's molecular, but that's wrong because it's just
It's because it's an
F4.
H plus, but
It's
hydrogen's a
technically both.
non-metal. That's why.
Yeah, hydrogen's a non-metal, but they're ionically bonded, which is why you'd consider it an ionic compound.
Yeah, ammonium chloride's a weird one. But I would just stick to, with what Dr. Alexander's showing, what we're showing you with our workbooks. Just like if you see two nonmetals, same molecular, even though this is like an exception you see there.
Yeah, these are exceptions. Because
So what are the answers that'll get us a good grade on our test?
I'm not a Dr. Alexander person. Someone answer that.
It'd be Dr. Alexander's. Yeah.
So, yeah, but what's the answer then?
That would be then covalent, because it would be all of those like hydrogen, sulfur, and oxygen. All of them are non-metals.
I don't like these questions.
Me neither. They're trick ones.
They don't like that they're tricky. Yeah. So
that last one is molecular?
Yeah, it is molecular. According to his answer key, it is molecular, although it does have ionic characteristics because of the charges. Yeah, I wish you would put in an explanation for that one. All right.
I think it's because you can make an argument both ways, but
yeah.
at the end of the day, if you go to like the super literal definition, they're all nonmetals, so it's a molecular compound. I guess that's his argument.
You guys see him one more time before the exam, like before you need to take the exam. So I would suggest just running it by him just to get his input on it. That way you can like argue with him. Like, let's say he says it is ionic and like you get it wrong, then you can tell him like, oh, but you said. That way you can have his actual words. So talk to him about it on Friday for sure. Does that make sense?
Is there any other questions? That way I can do number 4 as well.
So for the second to the last with the ammonium chloride, do we just leave that as ionic, or do we just like leave out the exceptions?
I would leave it as ionic because that's how he has it stated also in his answer key. So yeah, I would leave it as ionic. So ammonium chloride is ionic and molecular for sulfuric acid.
Okay, got it. Thank you.
No problem. All right, I'm gonna go ahead and clear the board real quick. We have like 15 minutes. Okay. So, next question states, what is the name of a compound containing magnesium ion and a phosphate ion? Wait. Yes. So we have magnesium present, and we're given our charge of +2. And then we have phosphates. How many oxygens does phosphate have? I know it's given, but
4.
4.
yeah. In our charge?
Maybe
Negative.
Yeah, -3. All right, and then, so how would we write out this formula? We'll write them next to each other. So how would I write it out?
Would it be Mg3 and then PO4 2?
And why don't I just multiply everything by 2? Why don't I just have P2O8? Why is that wrong?
Because it would tell you that you have 8 oxygens.
We technically do have 8 oxygens present.
But like you wouldn't, I mean, it wouldn't be like with the phosphorus one?
It's mostly, we need to identify what phosphate is. So that's why we leave it in parentheses. That's why we leave it as its own compound. So phosphate ion is its own compound. That's why we don't distribute the 2 whenever we write it. But yeah, this is correct. Okay, is there any questions on that one? And the next question is basically the same as this one. It's just asking for the name. Do we need it? Does someone want to cover 6?
So the rule of 7 can combine non-metal with metals.
So our rule of 7, that is, we have
Like the one that you did, Mg and then phosphate. Phosphate is on the rule of 7 and Mg, it's a metal if I'm not wrong.
Okay, so you are correct about magnesium. Magnesium is a metal, but phosphate doesn't follow the rule of 7.
It doesn't?
No, it does not. Phosphate is in this little box here. It's in the little box that's right underneath.
Oh, okay,
yeah.
okay.
This little box doesn't follow the rule of 7. They follow the normal charges that the other, the normal charges that the periodic table has. So that's phosphorus, sulfur, I believe arsenic, and selenium.
Oh, okay.
The ones that do follow the rule of 7 would be boron, carbon, nitrogen. And then we have chlorine. Shoot, I forget the order of the periodic table. Chlorine, bromine, iodine, and yttrium. These 7, let me highlight them. These 7 do follow the rule of 7.
Okay.
And to answer your other question, yes, they can make bonds with metals because they have a charge. And the only other way they can make a bond is by making an ionic bond with a metal.
Okay, thank you.
No problem. Any other questions? That way someone else can take over.
Wait, so did we, what is this called again? I'm sorry.
This, are you referring to this portion? Sorry.
No, I'm referring to like the question 5, like what's the answer?
Oh, question 5. Oh, so I guess we can go to that one too. Question 5 is asking for, so what is the name of the compound containing a magnesium ion and a phosphate ion? So magnesium, what's the charge of magnesium?
2 plus.
And then what's phosphate? Can someone tell me the formula?
3 minus.
I'm sorry?
It's a
3 minus.
Oh, yeah, 3 minus, yes. So 3 minus, and then what would be the name of this compound?
An ionic compound.
Not
Magnesium
the
phosphate.
molecule, but the name.
Phosphate.
Magnesium phosphate.
Yes, yes, it would be.
Phosphate.
So magnesium, that's Mg. So the answer to number 5 is magnesium phosphates. There you go.
So we just put the names together.
Yeah,
when it asks
yeah.
something.
5 and 4 are basically the same question. Just,
Okay.
Mhm. I think we're good. Okay. Do you guys want me to cover 6 as well?
I'll go over the other ones. Okay, guys. So which fundamental particle has an electric charge of +1 and a mass of 1?
Protons.
Yes, exactly. And these are most likely will be on the exam because I've taken it with Dr. Alexander. So yes, it's protons. Okay, so which fundamental particle has an electric charge of -1 and doesn't really have any mass? It's like really, really small.
Electron.
Yes. And then which one, I know we're going this one, which one has no charge but has also an atomic mass of 1?
Neutrons.
And when we're talking about the mass of an element, what makes up the mass?
The protons and the neutrons together.
Yes, exactly. So the mass of an element, I don't know why I'm writing crooked, but I can't write like this, is made up of the protons and the neutrons.
But that's just like the mass number, right? Because the atomic number is something else.
Yes, exactly. So let me just give you an example, like with carbon. So the atomic number would be 6 because atomic number is the same thing as what?
The number of protons.
Yeah, so atomic number is the same thing as, what did that delete? Oh, never mind. Okay, atomic number. It's the same thing as protons. So if in the exam it tells you something like, give me the atomic number of oxygen, just know that is referring to protons. And I've seen it before on past exams where Dr. Alexander actually puts it in a different way. So you could see it in your periodic table that this gives you the protons or the atomic number. And then over here gives you the mass, right? But you could also see it another way, which looks like this, which is, oh my gosh, why did it do 2 C's? Anyways, you know the other way it could also be shown? Does anyone know? Like the same thing.
It puts the
yeah,
other one on top.
The 12
Yes.
and then the 6.
Yes, exactly. So it's gonna put the mass up here instead, and then the atomic number down here. So just keep that in mind, okay? Because he might give you something like this and say, give me the atomic number and then give me the neutrons. So just know this is your mass and this is your protons.
And then like the atomic mass and the actual mass can be different because of the different, I forgot what it was, but it was in something.
Yes, exactly. Okie dokie. Yeah, they can be different, the atomic and the molecular mass. Okay, so moving, does everyone get this, by the way? Just, you know?
Yeah.
Yeah, okay. So what is the atomic number of sodium? So what symbol is used for sodium?
Na.
Yeah, it's Na. And remember, atomic number refers to protons. So how many protons does sodium have?
11.
Awesome, yeah. It has 11. And it says, what is the atomic mass of sodium?
22.991.
Yeah, exactly. So I'm just gonna put it down here, 22.99. Honestly, you could round, but just 22.99 right now. Okay, so moving on to number 8. Sodium consists of only one isotope. What is the mass number of this isotope? Wait, what is the other isotope of sodium? I know there's another one, but.
Well, it's kind of a question, but I answered my own question. It's a 789. Like, again, sorry.
Excuse me?
789 repeats on the question.
789. Oh, you're right. Oh my gosh.
When you said 8, I was very confused, but never mind.
Okay. What is this? What's the isotope? Okay, first let me say, what's an isotope? What's the only thing that makes an isotope different from the rest? Because the only isotopes I know is like these. What's an isotope, guys?
The number of protons that they have.
Yeah, so isotopes don't.
Oh, I was gonna say that the protons don't change.
Yeah, the protons don't change in isotopes, exactly. So they're always gonna stay the same because protons, that's what labels the element. So if we're talking about isotopes, what's the only thing that changes?
The molecular mass? The mass?
Yes, it would be the mass. So what makes up the mass? It would be protons and neutrons, right? So the only thing, yeah, so the only thing that's gonna change in isotopes would be the neutrons. I don't know how to spell neutrons. Okay, just know that the neutrons are the only thing that change in isotopes. And the way isotopes are represented would be like this, like that. Any questions on that? And by any chance, did anyone get this, what sodium, the only sodium isotope that there is? By any chance? No, I'll just Google it quickly.
The mass number would be 23?
It says there's 13. Guys, what's the, it says the only isotope for sodium. What would be that one? Because I don't know it.
I don't know either, but my guess would be like sodium 12.
Okay.
Let me look it
probably
up.
24. Because
24?
Yeah, because it's done based off of the atomic mass, the isotope number.
Okay. So I'm just gonna, okay, thank you. So this one would be like your regular sodium that has 11 protons and 12 neutrons, but then this is the only isotope that changes. So again, protons don't change. So how many does sodium have?
11.
Yeah. And then, whoa, my thing. Okay, so how many electrons does it have?
11.
Yeah, 11. And then how many neutrons does this isotope right here have? The sodium 24.
19.
Excuse me, how many? Someone say 13 because I didn't hear that one. I need to raise up my volume. It'd be 13. Yes. Yes. Yeah, that's the answer for that one. And the other one's just kind of repeat. How many protons are located in the nucleus of a sodium atom? Again, it'd be 11.
Actually, 10 would be different, like that last one.
How many neutrons are located in the nucleus of a sodium atom?
Yeah, that the isotope.
What do you mean by, is it talking about the isotope?
No, it's talking about the atom.
13 would be the isotope.
So how many?
By the way, Google says sodium 24.
Oh, I just figured that's what it was because of rounding. But yeah, so it says sodium atom. how many neutrons. So basically what you're doing is you're looking at the atomic mass and subtracting the number of protons. So how many neutrons would there be for this one, for the sodium atom? It would be what?
Wait, can you
Are you
repeat
talking
that?
about for the isotope or
No,
the
we're looking at
neutral?
the actual atom.
So just the neutral, like
Yeah, neutral.
um.
So sodium 23 basically.
Oh, okay. So you would have 12.
12, right? Yeah, 12. Wow. And that's pretty much, we have 1, 2, 3, 4, 5, 6, 7, 8 more questions, and we only have 3 minutes. So I guess that's it.
Just real quick, can you explain 11?
Yeah. Oh, 11?
Well, it says 11, but yeah, that one right there. The one
The
above
give an
it.
example of an element, that one? All right. So give an example of an element that has more than one abundant isotope. Honestly, the most obvious one for us would be carbon. And the only reason I say carbon is because we use carbon 12 is what we use like in everyday life. And then there's carbon 13, which we use for carbon dating. And then we use carbon 14, which is used for like radioactive, like more high-tech type, quote unquote, carbon dating.
Okay, thank you.
I think it would just be better to just give that one out for you guys, just so you know. And then,
It's the most commonly known one, I think.
yeah, I think that's the most commonly known one. And I'm just gonna skip quickly to, I guess, out of the remaining ones, which one do you guys want me to go over?
I would say 17, but you guys can disagree with me.
17 or 13?
17, unless anybody else like has one that they really need.
Well, okay, so for 17, it's asking for the formula of an ionic compound that has a sodium and an oxide ion. So basically what we're doing is we're getting a sodium ion and then an oxide ion, and then we make a formula from that. So bring that down. So in order for them to be balanced, we would need 2 sodiums for every 1 oxide, because oxide has a 2- charge and sodium has a +1 charge. That balances it out.
And is it oxide? Is it like IDE?
Yes. So for ionic, actually for all naming in general, for covalent and ionic, the second word will always end in IDE. IDE.
And that just indicates that it's in a bond. So in this
Yes.
case, it's oxide, so it's in a bond with sodium. And then if it were a covalent bond, it would still be oxide because it's in a bond with another nonmetal.
Yeah.
Like in water.
Yep. So any other questions? Because that is officially time.
Not from me.